postulate, second postulate states that angular momentum of the electron orbiting around the nucleus is quantized. That is, Ln is equal to nh by 2 pi, where n is equal to 1, 2, 3, etc. Why should the angular momentum have only those values that are integral multiples of h by 2 pi? Louis de Broglie explained this puzzle in 1923. We have studied about the de Broglie hypothesis that material particles such as electron also have a wave nature. Davison and Germer experimentally verified the wave nature of electron in 1927. Louis de Broglie argued that the electron is in its circular orbit as proposed by Bohr must be seen as a particle wave. In analogy to waves traveling on a string, a particles too can load to standing waves under resonant conditions. We know that when a string is plucked, a vast number of wavelengths are excited. However, only those wavelengths survive which have nodes at the ends and from the standing wave in the string. It means that in a string, standing waves are formed when the total distance traveled by a wave down the string and back is one wavelength, two wavelength, or any integral number of wavelength. Waves with one other wavelength interfere with themselves upon reflection and their amplitudes quickly drops to zero. For an electron moving in nth circular orbit of radius Rn, the total distance is the circumference of the orbit, 2 pi Rn. Thus 2 pi Rn is equal to n lambda, where n is equal to 1, 2, 3, etc. We have lambda is equal to h by p, where p is the magnitude of the electron's momentum. If the speed of free electron is much less than the speed of light, the momentum is mvn. Thus, lambda is equal to h by mvn. From these equations, 2 pi Rn is equal to nh by mvn, or mvn Rn is equal to nh by 2 pi. This is the quantum condition proposed by Bohr for the angular momentum of the electron. We saw that this equation is the basis of explaining the discrete orbits and energy levels in hydrogen atom. Thus, de Broglie hypothesis provided an explanation for Bohr's second postulate for the quantization of angular momentum of the orbiting electron. The quantized electron orbits and energy states are due to the wave nature of the electron, and only resonant standing waves can persist. Bohr model involving quantum trajectory picture correctly predict the features of the hydrogenic atom. In particular, the frequencies of the radiation emitted or selectively absorbed. This model, however, has many limitations. Some are: the Bohr model is applicable to hydrogenic atom. That's an important one. It cannot be extended even to mere 2 electron atoms such as helium. The analysis of atoms with more than one electron was attempted on the lines of Bohr's model for hydrogenic atom, but did not meet with any success. Difficulty lies in the fact that each electron interacts not only with the positive charged nucleus but also with all the other electrons. The formulation of Bohr model involves electrical force between positively charged nucleus and electron. It does not include electric force between electrons, which necessarily appear in multi-electron atom. The second postulate: while the Bohr's model correctly predicts the frequencies of the light emitted by hydrogenic atoms, the model is unable to explain the relative intensities of the frequencies in the spectrum. In emission spectrum of hydrogen, some of the visible frequencies have weak intensities and others strong. Why? Experimental observations depict that some transitions are more forward than the other. Bohr's model is unable to account for the intensity variations.